Okay. I hope you are able to see my screen. So till last class, we spent considerable amount of time in gate-based circuits. And otherwise, we spent time on combinational circuits, starting from Boolean expressions, K-map, and then different applications of combinational circuits, multiplexer, demultiplexer, encoder, decoders, right? So we saw till the last class. Today we will start with sequential circuits. What is the difference between a sequential circuit and a combinational circuit is there is only one simple fact, which is more important fact. What is that is in combinational circuits, you don't have a memory element, meaning that if you are giving some input to a combinational circuit block, it will immediately give you the outputs, which means that this output or this particular input, it is not stored, right? This is not stored. Whereas in case of sequential circuits, you will have the option to store, right? You can store the data. And not only that, you can use this stored data in your inputs also, right? So that is the difference between a combinational circuit and a sequential circuit. So the simple block diagram is given here. Before that, I'll just tell you the difference again, that in combinational circuit, your output will depend only on the input, which means that you did not have this memory block in case of combinational circuits. In sequential circuits, your output will not only depend on your input, but also it will depend on the previous input values, which means that this output will again be a part of its input in the next cycle, which means that it will have some kind of a memory to remember what was there in the previous state. Now, there are two classifications of sequential circuit. Either your sequential circuit can be synchronous or asynchronous. What do you mean by synchronous is all the operations inside your combinational circuit. I mean, you please remember here, this is the complete block is a sequential circuit here, which includes a combinational circuit that we studied till last class, plus a memory element. So this combinational circuit and memory element, everything will be synchronized. Everything will be synchronized, and synchronized how? Synchronized using a clock, right? If there is a one clock cycle, then everything will operate. In the next clock cycle, everything will operate again. So every sequence inside this combinational circuit will be synchronized using a clock. So those kind of sequential circuits are called as synchronous circuits. If there is no clock in your sequential circuit, then they are asynchronous circuit. So some examples of a sequential circuit, if you ask me to give, there are a lot of real life examples. I mean, anything that you come across which have some kind of a memory element, then that is a sequential circuit. A simple example is a lock, right? If you're having a number lock, then that particular number code is stored inside your lock, right? So that is an example of a sequential circuit. Or other terms is, say you are using a lift, okay, lift or even elevator. You are moving up and down, right? Which means that the exact position of different floors are stored inside this elevator. So you are able to go to the already stored value of your lift, stored position of your lift. This is one example again. So any application that can remember its state, its previous states, those can be called as the sequential circuit. More importantly, your computers are sequential. Your computers will operate based on the clock cycles, right? Why it is taking so much time to load your front desktop page? because there are sequential operations that takes place to reach you to that particular main Windows page. So hence your computers are sequential. Now every time we say we have already studied a lot about the combinational circuits. It is very important that you understand now what is a memory. Now when we say that it should have a memory, what are the characteristics of a memory? Anybody? Just can you unmute yourself and say what are the characteristics of a memory? What do you say that obviously it can store data, right? Any other characteristics of a memory? Anybody, can you unmute and say your answer? As always, no response. Okay, never mind. So when we say a memory, it should have three important characteristics. What are its characteristics are? First, it should hold its value. Hold means it should store its value. Then you must be able to read the value that is stored in the memory. And you must be able to change that particular value. A best example of a memory is the lift, right? If you are in, say for example, if you are using a lift and if you are in floor number 2, then it stores that particular value that it is the lift is at the second floor. When you are at the ground floor and if you see that your lift is in the second floor, you can read where it is, right? So and if you want to change it, then you press the ground floor calling button for your lift, then you are changing from 2 to ground floor. Right? So this is the best example which we can use it for a memory. Now, for the digital electronics sake, let us consider a simplest case of a 1-bit memory. So what do you mean by 1-bit memory? Again, it must satisfy all these characteristics. First, you must be able to store the bit. So what are the two values that your 1-bit memory can store? It can either store 0 or it can store 1. You will be able to read the bit also, and at the same time you will be able to change the bit. Here, if you are able to change the bit to 1, then what do we say? We say that we are setting the memory. We are setting the memory. If you are clearing the data and storing 0, then what do we say? We are resetting the memory, right? So you must understand the difference between setting and resetting. So if you are changing the bit, either you can set it to 0, or set it to 1, or you can reset it to 0, or reset the other name is you can clear the bit to 0. Okay. Now the important question comes here. All we have studied is what? Gates only, right? We have studied AND gate, we have studied OR gate, NOR gate, NOT gate, etc., which means a combinationals of gates only. How do you expect that these gates can remember its output or remember its states? So the question here is, how can a circuit remember anything when it is just gates that produces output according to the input, right? How do you make a circuit that performs the job of a memory? Please remember, our memory must be able to hold the data, read the data, and you must be able to change the data. Okay, so what is can anyone suggest an idea? How do you make simple circuits into gate circuits into a memory? Okay, I'm sorry, I should not have asked because you respond very well. Okay, fine. So the idea here is you must create a loop here, right? So the idea is you have to create a loop in a circuit so that your outputs are also inputs. A simple example here is I have shown here, right? So this is a simple example where your data is always available in the circuit. How? Say for example, you are storing 1 in your circuit. This is your circuit, right? I have looped this particular circuit. What will be this output? This will be 0. This will be 1. So always your output 1 will be there in the circuit. If you want to take the output, then take a tapping here and then take a tapping here. This tapping is Q and this tapping is Q bar. The same circuit can be redrawn like this, right? Is there any difference here? There is no difference. You see, I'm just going to highlight this. This is the Q line. This is the Q line. One tapping of your Q line has been taken and fed to another input of your inverter circuit. One tapping has been taken and fed to another input of your circuit where its output directly goes to Q bar. Where its output directly goes to Q bar. And its other input goes to the input of your inverter, right? So both the circuits are same. Okay. So this is an equivalent circuit. Now we have to check, do they satisfy our three criterias? What are our three criterias? Okay, it must hold the data. I think it is holding the data. Am I right? It must hold the data. First point. Second, you must be able to read the data. Can you read the data? Yes, you can. When you take a tapping like this, you can definitely read the data. Third, can you change the data? It is not possible here. Why? Because there are no inputs, right? So your output itself is an input here, but there are no explicit inputs, so you cannot change this data. Okay, so then how do you make a change? Yeah, this is all about what I said now. You have to first check whether this circuit remembers anything. Yes, it remembers the value of Q through a loop. Similarly, Q bar also it remembers. You can read the data by tapping outside, but we cannot change the data, right? So because there are no external inputs here, so we can't control whether Q is 1 or Q is 0. So out of the three, two things are done. So these kind of elements are called as latches. What do you mean by latches? They will respond to the inputs immediately, right? So these kind are called as latches, and these kind of circuits are level triggered circuits. What do you mean by level triggered circuit is they will always operate based on what is the level at the steady state of your value. Right? If this is your clock pulse, this is your clock pulse, this will not detect the change over here. This is changing from 0 to 1 and 1 to 0 here, right? These kind of circuits do not check for these changeovers, but they will always look at the stable values of these clock pulses. That is what is called as a level triggered circuit. Now, in order to include the third specification of ours where we can change the data, what we'll do is let us replace this two NOT gate with a NOR gate. So when we use a NOR gate, what will happen? Your NOR gate will have two inputs, right? So out of this, one of the inputs, let us use it for some external input, and the other input, let us use it something similar to this particular part. Similarly, on the bottom part also, we will have a NOR gate here. One we can use it as an input, and the other we can use it as the feedback circuit. So this will be our Q, this will be our Q bar. Okay, so in order to include the third condition that we must be able to change the data, we are going to provide inputs through NOR gates. So our circuit gets modified like this now. So this particular pin is R, this particular pin is S. Why R and S, why not A and B? Because there is a meaning to it. R represents that reset and S represents that it is set. For the sake of convenience, we are going to reuse this particular circuit again and again. So what I'll do is I will redraw this particular circuit here. I will redraw this circuit here. So just bear with me, there is some issues. Okay, right. This is your reset signal and this is your Q. And I have another NOR gate here where its output is Q bar and this feedback output, and the other input is yes. Okay, so please always remember this Q and Q bar, they are complement of each other. Okay, now if you write the Boolean expression for this, we are going to write now. Before that, Q and Q bar, they are the feedback in this particular circuit. So this will be your Q bar here, and this is going to be your Q. So what will be this particular Q? That is, let us assume that this is the next Q value, and this is your next Q bar value. So your next Q bar value can be written as R plus Q bar of the current value. Am I right? Q bar of the current value, the whole bar. Why? Because this is an OR gate. Similarly, this Q bar next can be written as S plus Q current the whole bar, because this is a NOR value. I'm just writing the Boolean expression at this particular point. Okay, right. So we are going to use this expression. Let me write here because this is very important expression. So my Q next will be equal to, I need to write the Boolean expression. My Q next is, and Q next bar will be equal to Q bar current plus your reset value, the whole bar. And this one is Q current plus yes, the whole bar. How did I write? Again, I am repeating. So this one is your Q, sorry, this one is your Q, and this one is your Q bar, right? So it takes 2 cycles for your output to come. In the first cycle, what happens? First, you will get some Q and Q bar value, and for your circuit to get stabilized, this Q and Q bar will be fed back to its input, and in the next cycle, that is in the second cycle, your Q and Q bar values will get stabilized. Okay, so this you must remember. Okay, now let us see different cases. What if when your S is equal to 0 and R is equal to 0? When your S is 0, right? When your S is 0 and your R is 0, right? And I do not know what is this Q and Q bar value. Your Q and Q bar value will be the current values here. So when this is 0, what will be your output? Your output, it will be same value, right? Because if you recall the NOR gate expression, it is 0 plus Q bar current, and its not will become Q bar current only, right? So if required, I'll just write the truth table for OR gate. Oh, very old system, so system got hanged or something. Just hold on. There is some problem with the system. defined. I'm sorry, there is system is too slow. This is not defined, right? So I'll just use another system. So by the time, just please hold on. So I'm just joining in another system.
So you're muted. Excuse me, sir. Sir, you're on mute.
I have no idea what's happening. It's a
Sir, now
system
you're
problem.
audible.
Additionally, the teams are is also creating an issue. So, okay. So I'm sorry, uh, both system and the software issues. All right. So our idea is to um, hold the data, right? And then we must be able to read the data and we must be able to change the data. So with the previous, with the inverter circuit, we were able to hold the data, we were able to read the data, but we were not able to change the data. So what we did was we replaced our inverter with a NOR gate. And with the NOR gate, so this is how the feedback mechanism is. Q and Q bar will be fed back to its input. So R stands for reset and S stands for set. Why set is here and reset is here, you will just understand now when we analyze this particular circuit. So the Boolean expression for the stable state can be written as Q next Q bar current plus R the whole inverter. Because why? For you to get the output here, you require 2 cycles minimum. How 2 cycles? When you are giving input here, right, you will get some random outputs across Q and Q bar. This input must be fed back to this particular input for the input of these NOR gates. And then to get a stabilized output, you require 2 gate cycles. When I say cycles, it is 2 gate cycles. Okay. Or 2 gate delays, you can say. Now let us analyze this particular circuit. When S is 0 and R is 0, what happens when S is 0 and R is 0? So it is a NOR gate, right? So your output will be your current value. So only this will decide now. So Q bar of current, the whole bar will be Q current, and Q bar of next state will be equal to Q bar of current state. So what is that you conclude from here is when your input is 0 and 0, then your output is same as that of your previous state, right? Your Q of your next state is same as that of your previous state. So this is what we say that it is storing its value. This is what we call it as a latch. It is latching its value. Okay. Now let us look at the other input. When S is 1 and R is 0. When S is 1, we say that we are setting the latch. We will see how. So when S is 1, what happens? Look at the Boolean expression here. Please, I'm not writing it again. So when S is 1, what will happen? This will be 1, right? This will be 1. So any So your Q next bar will be equal to 0, right? Regardless of whatever it is your Q current value, your Q next bar will be 0. So your Q bar next will be 0. And if this particular 0 goes to, if this 0 goes as an input here, what will be your output? Your output now will become 0. Your current value for your Q bar next, Q bar will be 0. And your reset is already 0 here. Your reset is already 0 here. So 0 plus 0 and the whole bar will be 1. So to conclude here, when your S and R is 1 and 0, your Q bar will become 0 and Q will become 1. So I'm just creating a parallelly a truth table also, right? So when I'm having S, R, 0 and what is my output Q and Q bar? Okay, so when it is 0 and 0, I'm not having any change in my Q and Q bar values. It is having my previous values only. When my set is 1 and my reset is 0, my Q is 1 and my Q bar is 0. So this particular state is called as the stable state. And here is, let us also understand the delay that it will take. I've already said you about that it will take 2 gate delays, but however, just for the sake of uh, the theoretical explanation part, let me repeat that. So when your SR is 1 and 0, it will take 2 gate delays for you to get a stable output. That is, when it is at 0 time, you will have Q bar is 0 and Q bar equal to 1. Just initially we are setting it. Why Q is 0 and Q bar is 1? Just for to start with, right? So your output will be, if Q is 0, then obviously your Q bar will be equal to 1 only, right? So this is the initial state. At time 1 t equal to 1 time second, you are giving a set input of 1. When your set input is 1, what will happen? This Q bar will change to 0 and this particular 0 will be fed back to your NOR gate here. Okay, so this will happen in the first time seconds or first gate delay. In the second time second, what happened is whatever it is the input across this NOR gate will go to the output. So in the second time cycle. So now this change in this Q bar along with this reset button R equal to 0 will cause a change in Q equal to 1. Okay, so only after time seconds you will have a complemented outputs. So the same can be one. So at 3 time seconds you can see that your latch will stabilize into uh, stabilize with S and R values. So a time cycle is given. That is what happens is initially at time 0 seconds, we are setting the latch and we are when S is 0, when R is 1. So this is 1 and this is 0 throughout. So what will happen to Q bar? So Q is initially 0 and Q bar is 1. In the first time cycle, you are because of this set equal to 1 here, Q bar will change to 0. because your Q bar here will be fed to the first NOR gate along with this reset signal, this Q value now will change to 1 here. So after 3 time cycles, all these states will be a stable state. Okay. So now let us look at the third input where we are resetting the latch. Resetting the latch means your R is 1 and S is 0. Again, when R is 1, this will affect your Q value. So Q next will be equal to 1 plus Q bar current, the whole 1. So 1 plus anything is 1, 1 the whole bar is 0. So now in the first time cycle, your Q next is 0. So what must be your Q bar? Q bar must go to 0. So let us see whether, sorry, it must go to 1. So this new value of Q will go to the bottom NOR gate and it will set your Q bar to 1. So now let me add one more row to this particular truth table that I just wrote here. When it is set is 0 and reset is 1, my Q bar is 1 and Q is 0 here. Okay. So okay. So now we can conclude here that when SR is 0, 1, your Q is 0 and Q bar is 1. This state we call it as a reset or a clear state. R stands for reset and S stands for set. And they will require 2 gate delays before your actual output gets stabilized. So this is called as an SR latch memory. Okay. Now, if you draw the characteristic table, so this table that I just drew now, it is a characteristic table. Characteristic table means it will give you an overall picture of how your SR latch will behave. So when your S and R are 0 and 0, there is no change in your output. That is, your previous state output will follow. When your S and R are 0 and 1, you will have your Q output as 0. Q bar output is obviously complementary, right? So you need not explicitly write it for Q bar. And when it is 1 and 0, your Q will be set to 1 and Q bar will be set to 0. So these are called as the states of a latch. This output that you are seeing here, these are called as the state of a latch. If required, for a better understanding, you can expand this characteristic table into a state table, right? What do you mean by state table? A state table will give you all possible inputs that will include the previous state and the current state output. So this will give you the previous state and the current state output. Let us see when your inputs are 0 and 0, right? And just for the to start with, we are assuming that our current Q bar value is 0 and 1. What will happen to your next state when your when your SR is 0 and 0, there must not be any change from your previous state values for your Q and Q bar. So if there is no change, it means same 0, 1 will be repeating here and 1, 0 will be repeating here. When it is 0, 1, what happens is your Q is set to 0 and Q bar is set to 1, whatever may be the previous state. Let our previous state will be 0, 1, still your output is set to 0, 1. Even your current state is 1 and 0 here, still your output across your SR will be set to 0 and 1, whatever may be your previous state, because your inputs are 0 and 1. Similarly, 1 and 0, whatever may be your current state, your output, your next state will be set to 1, 0 here and 1, 0 here, whether it may be 0, 1 or it may be 1, 0. So this is how we are resetting here. We are resetting here. Here we are setting here, setting our latch. Now we have been studying only 3 possible combination. What will happen to 1, 1? This 1, 1 is a peculiar characteristics, which means that you must not make your SR flip-flop go to 1, 1 at all. Why? Because this will give you a contradictory outputs. Let us see how it gives us a contradictory output. We know that in all these cases, if you see, if Q is 0, your Q bar will be 1. If your Q is 1, your Q bar will be 0, right? In all these cases, you can see here 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, right? So this is how your output will be contradictory. So this is how your output will be contradictory. very bad day for me. Okay, I've lost a lot of time today. Okay, all right. So another problem that you get here is it will get into a loop, meaning if you set R and S to be 1, you get Q and Q bar to be 0, 1, 0. Again, when when you make your S and R to be 0 and 0, already your current state is 0 here and 0 here. So your Q and Q bar will go to 1 and 1 here. So what will happen is this will keep on continuing. The circuit will enter into an infinite loop. You see here, initially when you set your R and S to be 1, this becomes Q and Q bar will be 0, 1, 0. This 0 and 0 now will be fed back here. And when you set and reset to 0, your output will become 1 and 1. Again, this 1 and 1 will be fed like this, and your reset will be 1 and 1. So this will enter into an infinite loop. Hence, your SR equal to 1 1 must always be avoided. So so what people thought is how do we avoid this SR equal to 1 1? So people thought that they should try with a NAND gate. So you know that NAND and NOR are complement of each other. Am I right? So what people thought is when you replace this with a NAND, then you have to replace your SR input also with their complements. So now this will become S and this will become R, and it is going to be I'm not sure what's happening today. Okay, so your S and R now will be complement of each other. So their inputs will also get complemented and your truth table will get reversed, which means you have to avoid 0 0 when you are using an AND gate. And for 1 1, you will have no change. When it is 1 and 0, it is a reset state. And when it is 1 and 1, it is a AND state. So this will become AND gate. So So we had a gated SR latch. So you had an SR latch, but with a control input also, right? So you are having a control input. Now what will happen is assume that this control input is always 1, right? So when whatever may be the input here, it will be complemented and it will be available to your S bar R bar latch. So I think it is time. We will continue from this gated SR latch in the next class. Uh, right. Sorry about today's net connections. So we'll see in the next class. Thank you so much.